Welcome back to Derivatives and Risk Education. In the previous video, we defined a finite probability space. It consists of a sample space omega, which contains a set of outcomes, and a probability measure p, which assigns a probability to each outcome. In this video, we'll build on that foundation by introducing random variables, which are functions from omega to the real numbers. We'll look at their distributions and expectations. Let's begin with the formal definition. Let omega p be a finite probability space. Then a random variable x is a function from the sample space to the real numbers. In simple terms, a random variable assigns a number to each outcome in the sample space. Note that a random variable is not random in the chaotic sense. It's a well-defined function. Here's an example from finance. Suppose we define a stock price model, where the full sample space consists of all the possible outcomes from 3 coin tosses, with each toss either heads or tails. So each outcome is a sequence like heads, heads, tails or tails, tails, heads. Now let's define a random variable, say the stock price at time 2. That depends only on the first 2 tosses. And let's say the initial price is 4. Then we define the price at time 2 as follows. If the first 2 tosses are heads, the price goes up. If they're mixed, the price stays flat. And if both are tails, the price goes down. Even though the full outcome includes 3 tosses, this particular random variable only depends on the first 2. That's totally valid. A random variable doesn't have to use all of omega. And the initial price, as naught, is constant, always 4, so it's called a degenerate random variable. Let's define 2 more random variables. X is the total number of heads, and y is the total number of tails. Each is a function from the sample space omega to the real numbers. This just means each of these random variables takes an event as an input and has a number as an output. X is the total number of heads from 3 coin tosses. So for the event HHH, the random variable function returns 3. Similarly, for HHT, it returns 2, as this outcome has 2 heads, and so on. Then for Y, which is the number of tails, HHH has no tails, so returns 0. And similarly for the other outcomes. Notice that we didn't need probabilities to define the random variables x and y. But once we assign a probability measure, we can compute their distributions. Probabilities that the random variables take specific values. So the distribution of a random variable x is given by the function shown here. This means the probability that the random variable big X has as an output the particular value little x equals the probability that an event in the sample space has the value of little x as an output of the random variable. For example, under the uniform probability measure, where each outcome is equally likely, and here we have 8 possible outcomes for 3 coin tosses, so each has probability 1 over 8, the probability distribution looks like this. P x equals 0 is the probability of no heads, so this occurs only for the single outcome tails, tails, tails. So the probability of this is 1 over 8. Similarly, we can get exactly 1 heads in 3 outcomes, so the probability of x equals 1 is 3 over 8. Note we often write p x equals j as shorthand for the probability that x takes the value j. It really means the probability of all outcomes omega such that x omega equals j. As can be seen below, y has the same distribution as x under the uniform probability measure, even though it counts tails instead of heads. But if we change the probability measure, say heads have probability 2/3 and tails 1/3, then the distribution changes. X still counts heads, but the probabilities shift. On the left, we see the distribution when the probability of heads equals a half, which is what we have seen before. On the right is the distribution for x when the probability of heads is instead 2/3. For example, then the probability that x equals 0, so when number of heads is 0, which is when we have only tails, is 1 over 3 cubed, so 1 out of 27. And in the same way, we can calculate other probabilities under this different measure. This distinction is crucial in finance. The random variable, like a payoff or stock price, stays the same, but its distribution depends on the probability measure, whether it's historical or risk neutral. Now, let's define expectation. Let x be a random variable on the finite sample space omega p, expectation of x, then defined as shown here. This means each outcome, little omega, in the sample space big omega, we calculate the output of the random variable x and multiply this output by the probability of the outcome occurring. Then we sum over all outcomes. Expectation is linear. This means that the expectation of constant a times random variable x plus constant b times random variable y equals a times the expectation of x plus b times the expectation of y. Similarly, if we apply a linear function to x, like f of x equals ax plus b, so we multiply the outcome of x by a and then add b, then the expectation of this function is just a function of the expectation. We'll define variance later. It measures how spread out the values of a random variable are around their expectation. To recap, a random variable is a function from outcomes to numbers. Its distribution is the probability profile of those values. Expectation is the weighted average. Changing the probability measure changes the distribution, not the random variable. In the next video, we'll explore conditional expectation, how to update probabilities and expectations when new information arrives. Thanks for watching, and don't forget to like, subscribe, and share with anyone learning financial math.